Hello, and welcome to the lecture on inquiry, scientific design, and statistics. The first part of this lecture is probably going to be review because you've all taken a science class before. But once we get into statistics and the role of statistics in scientific inquiry, this is probably going to be new content for most, if not all of you. And so the first half of lecture is just going to be, like I said, a lot of review, controls, and constants and variables. It does get more complicated as we get into that second part. So as you're following along and answering your notes questions out of your workbook, pause the video, rewind it, make sure you're going through at a pace that works for you, and you're doing your best to answer those questions thoroughly so that when you come to class, you're prepared to use that information. So, like I was just saying, most of you know what the scientific method is because this is your very typical first day of any science class at the high school level. And the goal of any scientific investigation is to obtain and interpret reliable scientific data. The goal is to get good data. If you don't have good data, you can't answer questions, which is really what the scientific method is about. And so in order for you to obtain and interpret data, we have this method of investigating questions, and this method is called the scientific method, and it has certain steps, and you've learned those steps in all of your science courses. And here they are. First, you're going to make some observations. And this is something that often is skipped, especially at the high school level where, your teacher maybe gave you a question that you're supposed to be investigating or something like that. And so that make observation step is something that's often skipped. But in essence, in quote unquote real science, a scientist has to see something that they're trying to understand. They have to start by going, I wonder why that is. And then once you've made those observations, then you write that question, and it has to be testable and it has to be data driven. Otherwise, then that's something that you would investigate more kind of in the humanities. And then you form a scientific hypothesis, and that scientific hypothesis is a statement that could answer the question. It needs to be testable, it needs to be falsifiable. In some of your other classes, you may have heard that if you do this if, then, because form for a hypothesis, if I do this, then this will happen because, and then you tell me why. That's not a terrible approach, but it's kind of gives you a false sense of security. It is possible to write an if-then-because statement that is not a hypothesis, that is a prediction. And so you want to be careful that the if and then part of your statement is helping you form a very solid because. The because is the part that is kind of your hypothesis as to why something is happening. And so you want to be careful with that. Once you have this hypothesis, then you test it by collecting data and observations. And then this next step right here is going to be the step that is new for almost everybody, data analysis. And you might be looking at the data analysis line here and saying, I know how to do a graph. That's true, but almost none of you have ever actually had to take data and do statistical analysis that allow you to determine patterns. That is probably going to be new, and that is going to be the focus of the entire second half of this PowerPoint. It's not just about making a graph. I know you guys know how to make a graph, but interpreting that graph in a scientific manner is a very different task, and it's a much more difficult task. Once you've done your data analysis, then and only then are you able to draw your conclusions. You interpret your data, you interpret your observations, and you support or refute that hypothesis that you came up with in the first place. The last thing I'm going to really highlight for you here is this thing down here on the bottom. In science, nothing can be proven, it can only be supported. What I mean by that is that we cannot in science prove anything completely. We can support things, we can collect data in order to refute things, but we can never prove something to be true. And so, in your notes questions, I have a giant box around this statement. We cannot prove anything. And if you write in a lab, this proves whatever, I'm going to circle it and put a big X through it. Nothing can be proven, only supported. And we'll get into the theory behind that in a little bit. Variables, this is probably review for you. So in any kind of scientific investigation, you're going to have variables, things that are changing in an experiment. And those changes could be part of your experimental design, or they could be something that you're measuring in order to answer your question. Two kinds of variables. You have the independent variable and the dependent variable. That independent variable are the ones, that's the one that's controlled or chosen as levels by the scientists before you collect the data. And so maybe you're going to do measuring rate of change over temperature. Oh, that's not the right thing to use. Maybe you're trying to measure rate of change based on temperature. And so you have your graph, and you would have temperature down here. Sorry, my handwriting sucks with this. And then you have, rate of change, whatever. Your independent variable is the temperature. Before you started your investigation, you decided the levels of temperature you were going to investigate, or you should have. Maybe you were going to investigate the rate of change at 5 degrees and 10 degrees and 15 degrees and 20 degrees. Before you collected any data, you would have decided what those temperatures are. And so that is your independent variable, the things that were chosen by the scientists before you really even got started. The dependent variable are the things that were measured or observed. So I'm measuring rate of change in that particular example. And so on a graph, the independent axis is your x-axis. That's where your independent variable goes. Dependent variable is the y-axis. That's where your dependent variable goes. So you can use this bottom sentence, the blank depends on the blank, to figure out which is which. Does the rate of change depend on the temperature? Or does the temperature depend on the rate of change? Well, no. The rate of change depends on the temperature. So the rate of change is your dependent variable, and your temperature is the independent variable. So you can use that sentence to kind of help figure that out. Constants and controls. These, again, are things that are often brought up the first day of any science class, and then you never hear about them again. Constant is something that you need to keep the same for the entire experiment, especially between different trials. You might hear things that are not called constant, you'd call them confounding variables. Things that you hold constant are things that could impact your data, and you want to make sure that they don't. So very often these are things like temperature. This would be different than the previous example where temperature was our independent variable, but maybe pressure or light or humidity or things like that, concentration of reactants. These sorts of things are things that could very well impact your data, and you want to make sure that they don't, because your goal is to assure the reader or whoever's evaluating your work that the changes in your dependent variable are due completely to your independent variable. Kind of coming off that same statement, we have a control. And a control is something that's used as a standard of comparison. A control is typically the same conditions as those experimental conditions, but without that independent variable. And they give you some kind of basis for comparison that allows you to claim, again, that these changes that you see in your dependent variable are likely due to that independent variable and nothing else. Controls are hard, and we'll work with them truly all year, getting you good at this, and trying to get you to recognize what is a valid control and what is a not a valid control. But it's something, again, that often in previous science classes, they tell you exists, and then you don't ever do anything with it. And in this class, it's going to be different. Observations, just a little bit of vocab here. Scientific observations could be qualitative or quantitative. Of course, this term qualitative is referencing qualities, and quantitative is referencing quantities. So qualitative observations are color, shape, texture, something like that. Quantitative refer to the quantity or the count or something. Really, you're just looking for a number. Quantitative observations involve a number. Qualitative observations are just going to be some kind of quality. Color is a good example of that. All right, so data analysis. So here's the thing with data analysis. If there isn't numerical support for a conclusion, actual values, it's very unlikely to be agreed upon by a scientific community, and most importantly, it's not likely going to be published. And if you're in the academic world, if you don't publish stuff, you get fired. So you gotta do what you have to do in order to get you published and keep your job. In order to do that, you have to do good science. And good science involves data analysis. Data analysis is the evidence and the support for your conclusions that you're going to use to deal with that scientific hypothesis and to assess the validity of your scientific hypothesis. Data analysis almost always involves statistics and the development of something called a p-value that indicates whether or not it is significant. And that's going to come up again in the second half of this lecture, which you guys are most likely going to be doing next class. But the data analysis component is what's going to actually allow you to draw legitimate conclusions that are going to be accepted by the scientific community. And it's the analogy I have for you is this. If you've ever worn a shirt and some people saw it as purple and some people saw it as red, then you know that qualitative things can be argued about because there really was no right answer to the red versus purple. But numbers are much more difficult to argue with. And so data analysis is our way of assigning values to data to be able to draw legitimate conclusions that are less likely to be as subjective as they would otherwise be. We're just going to talk real quick about graphing requirements. This shouldn't be anything new for you. You may need to always use graph paper. You need to always use a ruler. You need to have a good title. Title easily is just what's on the y-axis versus what's on the x-axis of whatever it is that you're investigating. Don't obsess about titles. Just do y versus x of whatever. You need to label your axes with units, and you need to evenly space them out. Clearly mark your data points, draw a line of best fit, and this is the one that is the kicker. Sometimes kids forget this. Anytime you extrapolate beyond that last data point, you have to do it with a dashed line. So here's what one looks like. Okay, you can see on here, here's our label and our numbers, or label and our units rather, label and units down here. We're also going to have evenly spaced numbers. We have a really good title up here at the top. You can see this is that dashed point, right? So this is our last data point. So anything beyond that must be dashed. No problem there either. So that's what a good graph looks like. Data tables. We're going to look at data tables. Believe it or not, I learned this not until I went to college myself. Data tables don't have vertical lines. They only have horizontal lines. And if you flip through a scientific journal, for the most part, that's the case, which is kind of funny. I'm certainly not going to be a stickler for that, but I just put it in there because sometimes it's kind of a quirky thing. Rules are the same as graphing. You need to have title, labels, units. Use a ruler. Make a neat data table. Don't just freehand it because that gets very messy and tricky to read. Depending on your data, you could put your independent variable on the left or across the top. So here's some samples of that. Here they are. Here's another trick to figuring out the difference between your independent and your dependent variable. The set of numbers you fill in before you collect the data or before you start your lab, that's your independent variable. And then the one that you have to fill in is your dependent variable. So this is two data tables that are exactly the same, right? You can see that the title is the same, the labels and the units are the same. It's just I did one that is set up horizontally and one that's set up vertically. There is not a right or wrong here. Do whatever fits best in the space that you have available to you. So at this point, you should be able to do the SpongeBob SquarePants questions that are in your notes questions. And this is going to be the end of the lecture from day one. And so if I split this lecture into two classes for you, here is going to be the end of that day one lecture. So this is going to be where you'll answer those questions, the SpongeBob questions, and then you're going to pick up with this next part next time.